when the full professors allowed me to start. It is my great...
Puedes empezar.
¿Puedo empezar?
Permiso.
Mira, de mi grupo alguno hay, pues a ver si aprendéis, veis que la jerarquía se mantiene, aunque pasen 15 años. Well, anyways, let's switch to English because this talk is being recorded and streamed over YouTube. So it is our great pleasure to host at the Donosti International Physics Center, Diego Romero Abujetas. I could say many things about Diego, but I'll keep it short. You did your PhD in CSIC, Instituto de Óptica, could be?
Estructura de la materia.
Estructura de la materia. It's always complicated for a non-CSIC person to talk CSIC with Sánchez Gil. And now Diego is in the University of Freiburg, working with Luis Froufe, another good friend of the Donosti International Physics Center. And with this, I leave the stage to you to teach us about forces in disordered systems.
Thank you for the presentation. First, I would like to say that I'm really happy. It's an honor for me to be here because I was here different times doing different internships. It's the first time that I want to do a seminar, so I'm very happy for that. So we are going to talk about optical random forces in the dipolar system, and I correct a typo in the talk. In the actual word iteration should be interaction, control colloidal interaction. I want to present a word done in collaboration with Gaussian Master. Is the PhD student and Luis Froufe Perez. I come from Freiburg, and the first thing I need to say.
You need to touch again, try a couple of times, and it usually from the computer.
Okay, that's it.
Okay.
Ahora sí.
Yes. I come from Freiburg in Switzerland. I would like to show you this slide because sometimes there is some confusion about the Freiburg in Switzerland or Freiburg in Germany. I come from Switzerland, this beautiful country with a beautiful landscape. It's a city between Bern and Lausanne. And as a very Swiss place, I show you a picture of the city from outside, from one of the entries of the city. You see the cathedral, the new town, the old town, and of course we are in Switzerland. We have cows everywhere around. Beautiful places. Going back to the work, I work in the physics department. I haven't any picture of the front view. This is the only picture I have in a cold day, in a winter cold day. And this is the group picture of the previous year. So some of the people have left. New people is in the group. And specifically, I working more closely with Augustin Master, is the PhD student, and Luis Froufe Perez is the principal researcher. So I would like to show you what is the outline of the talk. First, we're going to talk about a little bit a motivation introduction about optical forces. In colloidal system, it is a little bit fake because I'm not an expert in colloidal system. And in the end, for me, a colloidal system is a system of dipolar particles. Later, I'm going to show the theory about what is a random field, what is the way to calculate the optical forces, and what is the coupled dipole approximation we can use to describe this system. And later, we're going to finish to do some examples about how to use these tools to engineering the forces between particles. So let's go to the first part. I would like to highlight the electromagnetic force do induce optical forces because normally we don't take care about that. But I am the first that do that. I take my sample. My sample is a array of particles, and then I would like to calculate transmission, reflection. Then I have a sharp. I have a sharp window for transmission, a given frequency. This system is very nice. So if I shine light in this system, a freestanding system, of course, in the end, I will have optical forces, and the system are going to move. I'm going to have diffusions, and the system want to move to the equilibrium configuration. So we need to care these optical forces. It's true that in these specific cases, in the end, we don't have never a freestanding system. We have a substrate supporting our system, and instead to have a sphere, we have something like a disk. We have an array of disks, more physical, more easy to do experimentally. And then in this case, if we shine the system, we have something like that. But when you, if I know they have a strong resonance, it's a given frequency, Inside the system, there is optical forces, but in the system is attached, there is a stress, but if the optical field is not very high, there is no deformation and everything is okay. But since I would like to talk about optical forces, I'm more interested in this kind of system, no freestanding system or a bunch of particles floating away in a liquid on another medium. And this is more or less what is the definition of a colloid. Because in general, a colloid is a suspension of a phase in different phases. For example, one of the more famous colloid, or at least the colloid that people really like, is the milk. It's a suspension, it can be described like a fatty particles in water, and the people like because the milk is very white and it's not easy to get white colors. And in technology, industrial application, is interesting right now. The people want to remove the titanium dioxide in order to get another material. I don't know talk about this topic, but this is one of the reasons why the people like colloid or milk due to the property of this system. And if you see the milk in optical microscope, only a 40 times the amplification, you really can see the small particles that are floating away. And if you go even closer, you will see something like that. You have the fat particle, and there is a repulsive force between them that allow that you have the colloid, because if you don't have the repulsive interaction, the colloid cannot be formed, and then everything will precipitate. And there is an experiment, I don't know if you know about that, but in the moment that in the milk you have vinegar, you produce a transition, a phase transition, and you create a ricotta cheese. And then if you take the image of the same sample with vinegar and now a 5 times amplification, you cannot see anything else. There is a turbulent media, and you lost this some of the properties. And if you do again a closer view, the things that happen is the fat particle go together. This repulsive interaction disappears, and then the system produces a phase transition. And this is done using like a chemical, well, I don't know if chemical reaction, but the idea is if it is possible to induce this kind of interaction using optical fields. And go further in this analogy, colloids are a good systems to study the interaction, because you can control very well his property, and you can mimic another systems. So we can generalize this phase transition to another kind of phase transition induced by optical fields. With optical fields, it's possible to do a phase transition from a solid state to a liquid state, or to gas state, or go back and forth. You can do other things like change the correlation function between your particles, the dispersion of particles. You have a random system, you have a UP uniform. I'm going to describe later what is a UP uniform material, or even though create other kind of correlation function between your particles. And also regarding crystalline phase, depending on the property of your optical field, maybe if you have, for example, an array of particles and you add a new particle, you can control if the new particle going to be on top on the particle, on the new particle going to be in the middle of 2 particles, or be in the middle of 4 particles. That this can be seen like a cubic lattice, like I think it's a base center cube lattice or a FCC lattice. You can control. It's possible to control this kind of phase transition in a general way using optical forces. This is the question. And in order to try to do that in the future, first we need to understand how to control the optical forces between particles. So for doing that, I'm going to explain a little bit of theory. Hopefully you can follow me. It's not very fundamental. And first, I would like to describe what is a random field, because any field can be described as a sum of plane waves. This represents a plane wave propagating a given direction given by the vector u. And then the plane wave is the amplitude multiplied by a phase that depends on the direction propagation, and the amplitude can be decomposed into different polarizations, S polarized or P polarized. And a random field can be seen as an isotropic and homogeneous field that propagates in all directions. Then, in order to get a random field, it's like an integral over all different angle of propagation of the different plane waves. And also, in order to have also isotropy and homogeneity about polarization, we need to fulfill some relationship regarding the amplitude of the S and P wave. in this case, the relation is that the correlation of the S waves between S wave and the S wave and the P wave and P wave should be equal to the same magnitude for all incidents of the region. And well, the delta D this means that the correlation, the field are only correlated if they share the same direction of propagation. And the correlation between the S wave, the S part of the wave and the P part of the wave should be totally decorrelated, should be totally zero. In the moment that you have this, you fulfill this property, you have a random field. And now if you place a particle in this field, in principle, the average of the force is equal to zero. There is, this doesn't mean that the particle doesn't move. We know that there can be, even though the average is zero, there can be diffusion of the particle. But the important thing is that when we place more particles, now the forces can be different to zero. And we can manipulate what is the force between these particles using these random fields. Maybe this is very abstract. And to know what is a random field, maybe the best example of a random field are the vacuum fluctuation and the thermal fluctuation of the electromagnetic field. And the energy spectral density is given by the well-known black body radiation. This is the expression. The vacuum field or the thermal fluctuation field to the energy spectral density is, there is a component. This is the vacuum fluctuation, and this is the component related to the temperature of the medium. And in this specific case, if the constant I defined before, so this is the amplitude of your random field, is proportional to the energy spectral density of the black body radiation, we get the Casimir-Porter forces, or also the van der Waals forces. That is the short interaction limit. And then the idea to try to control the interaction with the particle is if we can engineer the amplitude of the field, or we can modify our energy spectral density to get the forces in which we are interested. So for doing that, we need to know what is the force between different particles. So this is very fundamental. The force is given by the Lorentz force. You have a charge in a given electromagnetic field. The force are going to be proportional to the magnitude of the charge and the speed of your particle. This expression can be generalized in the case we have a distribution of charges and current, and this is the integral of the charge distribution electromagnetic field and the current distribution and the curve of the magnetic field. And from this expression, you can get the forces. In the general way, I'm going to skip the first part. This is the general way. Okay. So this is the end of the talk. Thank you.
Mostrar de todos modos.
Okay, maybe it doesn't important because it's only to say, I want to see the next one because, no, maybe we need to check. A second. I'm going to download the presentation.
Your computer or
No, it's the
PC
computer.
You closed the PowerPoint? No.
Okay, hopefully it's work now. Okay, well, in the general way, we are talking about optical forces and how to calculate the optical forces between the particles. In the general way, the force can be the integral of these fields, and I would like to skip this part because we don't use it later. Only to say that instead to integrate the field in the particle, it's possible to write the force as an integral over the surface that surround a particle. So if we go to the optical forces in the dipole approximation, the way to calculate the forces is again use the Lorentz force, and then our system are going to be two charges of different sign separated by the distance s, and the wavelength operation should be much bigger than the separation of the charge. And then this object are going to have a dipole moment equal to the charge multiplied by the distance of the particles. And assuming that there is some kind of potential that link the particle together, it's possible to find the expression of the forces after the time average of the forces and some approximation, then telling that the particle doesn't move too fast. And another approximation, the force can be equal to the dot product of the dipole moment multiplied by the derivative of the field at the position of the dipole. This is the general expression for a time-dependent field, but in the case we have a monochromatic field, the expression modified to the real part of the conjugate of dipole moment multiplied by the derivative of the dipole moment. We are going to talk about using dipole approximation. Then our particle, the dipole moment of our particle are going to be a linear relationship with the incoming field given by the polarizability. And then the force finally going to be something like the field multiplied by the derivative of the field. This is the force in one particle, in one dipolar particle, but we need to know what is the incoming field in one particle, because our system are going to be something like that. The system are going to be described using a coupled dipole approximation. With all the system is a bunch of particles, a suspension of a small particle, very well described a coupled dipole approximation. So we have our particle around, we have an external field, and the field scattered by one of the particles, for example, the particle I. The field scattered at a given position in space is related to the green function that propagates the field from position of the position of the particle in another position, multiplied by the portability of the particle and the exciting field of the particle. But what is the exciting field of the particle? This is you need to solve this value. So the exciting field is written as the exciting field at a given particle I is equal to the external field at this position plus the scattering field of all the rest of the particles from position j to all. That is the green function that propagates the field from position j to position I, using all this sum proportional to the exciting field. This system is a linear system of equations that you can solve in order to get the exciting field. I'm going to spend a little bit of time to describe a little bit the notation I'm going to use. Hopefully, it's not very confusing. That this sum, instead to write in like a sum, I can write everything like a product of matrices. It's written something like that. Now it's like the green function that propagates the field for the position of all particles. This means the LP bar means the position of all particles in our system that propagate the field to the particle I, multiplied by a vector field that's going to have the information of all the field in all particles. If you, maybe it's a little bit abstract, but using a matrix representation of these tensors in which the electromagnetic field, the exciting field are going to be the field of first particle, the field of second particle. Using this basis, like this field, this object are going to be the field in one particle 1, particle 2, or particle 3. Then you can write this green function that go from all the particles to the particle I, can be like a row of green function that goes from particle 1 to particle I, from particle 2 to particle I, so forth. And also, since we need to remove the interaction of the particle with itself, because this interaction is already considered in the polarizability, we need to remove it. We are also assume that the green function that goes from the same position to the same position is equal to 0. This is not true, but using this approximation is the way to say, is the way to avoid the I equal j element. So using this notation, we can do again the same. No, this object was a 3-dimensional vector. Now it's a 3n-dimensional vector, where n is the number of particles. We can do the same with this vector here. This is a 3-dimensional vector. We can go to a n-dimensional vector particle and write something like that, where now this green function is like how the field propagates for all the particles, the position of the particle to the position of all the particles. And the matrix representation maybe is a little bit clear if I tell you that the matrix representation of this this big tensor is the green function that go to 1 to 1, that should be a 0, or the propagation to 2 to 1, the 3 to 1, the 2 to 1, so forth. So now it's easy to solve for a exciting field. We are able to compute what is the field in every single particle. And then is to solve the equation. If we rename this matrix as I call it A, and we can simply write something like the exciting field is proportional to the inverse of this matrix. This is for me, the DDA matrix. This is the matrix that tells you how all particles interact with each other. And then the exciting field is the inverse of DD matrix multiplied by the external field. So we know the external field, but for the optical forces, we need also the derivative of the field. I'm going to write the expression. Here is a vectoral component. This is the 3 component of the force. We focus in one component of the force. We can simply write like the one component of the force are going to be the field multiplied by the derivative of the field along this direction. The total force on all the system, the sum of all the forces are going to be the dot product of these big vectors. But if we want only the force in one specific particle, we can take always all the time the dot product of the specific field and the derivative of the field in a given particle. So we know the exciting field, and we need to know what is the derivative of the field. It is something interesting that the derivative of the scatter field now is only the derivative of the green function multiplied by the probability and the exciting field. It's important to know that from this step to this step, you don't need to derivate this object, because it makes no sense. Your particle is like a fixing position, you cannot derivate the position of the particle in this case. If you want more details, I can discuss later this step. But now we can do the same as before, and then the derivative of the field is the derivative of the incoming field, the derivative of the green function that connect of the particle, and the exciting field. We know the exciting field is the inverted PA matrix. So is this expression, we have everything. We know the exciting field, the derivative of the field, and now we are able to calculate the forces between the particles. And this will be the expression of the forces between our system of particles. Depend of the portability of your particle, the inverse DDA matrix, the incoming field, the derivative of the field, and the derivative of the green function. So it's good, but we have a small detail that we want to use this expression also for random fields, and we have a problem with a random field. A random field, you don't know what is the value of the field at a given position. You don't know the value of the derivative at a given position. You cannot use this expression in a random field. This expression, you can use it in a deterministic field. You can use it for a plane wave, a Gaussian beam, but not with a random field. You need to play a little bit around with the expression and then try to express the force as a function of the correlation between the fields. That is the thing that we can know. So using some manipulation and using the property of the trace, and also assuming we arrive to this expression with the force is totally proportional to the correlation of the field and derivative of the field and the correlation of the field. And then now this expression is general for any kind of field. If you know the correlation, you can calculate the forces. Doesn't matter if the field is a plane wave, a Gaussian beam, or a random field. Now you can calculate all the time his correlation and calculate the forces. Also tell you that in this approximation, of course, we say that the inverted DA matrix and the green function depend on the position of your particle. We assume that the particle doesn't move too fast. So we can take these matrices outside of the time average and only do the average of the electromagnetic field. Well, we have the total force, the total trace. This is going to be a big matrix, but the trace of this matrix tells you the forces. And also, if we want the force only in one particle, we know that the force in a specific particle are going to be the partial trace of this big matrix. So this matrix has information of the force in every single particle. And as I said before, this is general for any illumination field. And just for finishing with the theory part, tell you that we are going to be further with this expression of the force as a function of the correlation of the field. But if the field is totally random in thermodynamic equilibrium, the forces are conservative. So we can obtain a potential associated with these forces. And using the properties of the correlation between the field and the derivative of the field and the correlation of the field, Now we know that the correlation is proportional to the spectral density, the energy spectral density, and the imaginary part of the green function. And using this information, we can work out a little bit expression and finally arrive to this beautiful expression in which the potential between the particles is proportional to the energy spectral density and the trace of the log of the DDA matrix. It's interesting that now we don't have any, we don't need to invert the DDA matrix, but we need to do the log of the matrix. That this is the inversion of the matrix is the operation that mix and entangling of the particle. In this case, in the potential, the operation that entangling the particle are going to be the log of the matrix. If this is the potential at a specific frequency, if we want to know the full potential, we need to integrate along all the frequencies. And then the total potential is the integral of the power spectral density multiplied by the log of the DDA matrix. For sake of completeness, I'll show you here the DDA matrix. And then from now on, the idea is to how, depending on your system, are going to define what is the DDA matrix. I'm going to define the property of your system, and we're playing, knowing the system, we can play with the power spectral density in order to get the potential that we wish.
So U is the potential for the force.
Yes, if you derivate this potential regarding a position of a particle, gives you the force of this particle along this position.
And how does it disappear, the Green's function explicitly?
It's because the imaginary part of the green function, the correlation is proportional to the imaginary part of the green function, and here you can operate, because you can see, if you derivate this object, this is equal to the derivative of G multiplied by 1 over this object, something like that. And then this is equal, the force is the derivative of G multiplied by the inverse DDA matrix. It's something like that idea. When you place this expression here and you work a little bit. So we finally get the expression for the potential. We are going to use it to try to do some interesting examples. The first thing is to present you the particle we're going to use. All the time, we're going to use our canonical particle, going to be a spherical particle of diffractive index equal 3.5, the typical refractive index for semiconductor in the optical domain, infrared domain. And we are going to use this particle because I present you here the scattering cross section of the particle. And we can see that above this frequency, the system are going to be described very well by a dipolar approximation, because the green line represents the magnetic, it's like the magnetic dipole contribution of the response of the particle, and the red line is the electric dipole contribution of the response of the particle. We are going to use this expression, this particle, because we have strong resonances. I'm going to show you why this is important or is interesting in this case, because thanks to these resonances, we can create different potentials. Because we can see in this work from 2015 that using this expression, they calculate the potential at two different frequencies. Lambda when it's equal to 2000 nanometer or 1600 nanometer. They calculate the potential at these two frequencies. The red line is the low frequencies and the blue line high frequency. And you can see, well, in this case, it's true that the particle is the silicon particle, but places in water. So the resonance shifts a little bit, but the idea is still the same. You have strong resonances and you can describe by electric and magnetic dipole. Also told you it's true that I derive the expression only assuming that you have electric dipole, but it can be easily generalized when you include also the magnetic dipole. And then this author shows in this paper that changing the frequency, they can go from a very attractive intervention to a very repulsive intervention. And the thing is, and this repulsive intervention comes from to the interference between the electric and magnetic dipole, because this frequency is a little bit above these resonances, and then the dipole, the resonance is out of phase, and these interferences lead to this repulsive intervention. Then in this system, only by changing the frequency, we can go to attractive to repulsion. And then the idea is to do a linear combination of energy spectral density and get different potentials profiles. So all the time, I told you I'm going to use this particle all the time. In principle, we are going to focus what is the potential only between two particles. And if we change the particle, we need to redo all. No, so we need to, depending on the power spectral density will depend on the property of the particle that you are using.
That potential that you're giving there is not for random fields, or is
It's for random. Yes. So all the time we are focused in particles placed in random fields. Because we want random fields because they are homogeneous and then all the particles will feel the same.
so is that the average? Or...
The derivative of this potential gives you the average of the forces. This is the question.
But the derivative, I mean, that's not a function of x, that's whatever.
Well, yes, because this A is the inverse DDA matrix. Is written here that the A is a green function that depends on the position of all particles. So you derivate this the green function regarding the position of one of the particles is the thing I mean with the derivative. So this is the thing is that this is a vector element, a vectorial component, a multi-vectorial component because you can take the forces along different directions to all particles, and this is a number. But this number, you do the derivation regarding a given coordinate, you get the force or the force on this particle when you move along this given direction. So it's true now, all the time we are talking about the random fields, and it's possible to create this kind of field. In principle, it's possible. You can use a laser line and with the diffusers, you can try to generate this field. So the idea is we need to find the energy density distribution to get a specific potential. So we are going to solve like this equation. This is a sum of we are going to find what is the energy spectral distribution that gives you a given U. We have a small constraint is because if we have the constraint that the energy should be positive. And then this makes the things more difficult because if the energy could be negative, this field is very easy to do. But since you need to say that this origin is always positive, this complicated stuff. And this means that maybe it's not possible to fit to any potential in the world. You have some constraints. And then in order to try to get the best fit, we need to do, in our case, we use a non-negative least square algorithm. I'm going to show you the sample of fitting two different potentials. For example, if we have, we have two particles, when they go very close together in the hard sphere model, they experience like an exponential force. Then if we want to control balance this force, we can try to generate a potential that is proportional to the inverse of exponential. And then using this linear fit, we want to target this blue line, that is a exponential potential, and using this power spectral density, we are able to do this fit. So in this case, it's good, no? It's possible to get this potential. Can be interested to try to switch this particle. You want to go farther to know what happens when the particles go farther together. And this fits very well. But for example, I would like to fit another potential. This is the inverse, like a gravitational force, but a repulsive gravitational force. We try to fit this potential, and you can see that for this particle and for this energy density, that is in this basis, because we need to fix the frequency for doing the fit. The fit is not very well. You get something, yes, you get something like a 1/r, but with a lot of oscillation. So it's not possible all the time to get a good fitting. In this case, okay. In this case, it's not good. And then we would like to do something more fundamental to say, okay, I have this particle, I have this range of potential, I have this range of distance, and then which potential we can fit and we can do. And this is something we can do in the future is I can give a recipe of what we can do and what we cannot.
So what do you think the inset? I don't understand what this is.
The inset means what is the value of the power spectral density we use to get the potential. For example, if we do a linear combination of this line of energies, we will get this potential.
So you just choose a few frequencies or something like that.
Yeah, the idea is to try to fit with less lines possible, because in the end, experimentally, you need a lot of power. You need to divide the power in different laser lines.
And they are chosen so that you get the potential, or they are chosen because they are from a black body, or
No, they are chosen in order to get a potential. And we do a non-negative least square algorithm because the energy should be positive. This is one of the constraints.
so the algorithm is the one that gives you what are the lines that
Yes,
fits the.
this is it's a linear fitting. You can play with some variable. For example, you can also in the fitting you can try to minimize the number of lines, and then you need to add a new term trying to minimize the system. But this is a fitting. No, I want to fit this potential, and then using some constraint, I tell me if I use this energy distribution, I get this potential. So it's very good. But if I use this distribution, this is the best potential I get. And then it's not very good. And then we need to look further which potential is possible to do it, and what of them are not possible to do. So, and this potential maybe can be useful to generate stealthy uniform point patterns in real space, because I'm going to explain you a little bit what does mean a uniformity. Here I present you your two pattern system. The first one is a total disorder system. I think it's the hard sphere model. And this case is a disorder but uniform. By eyes, it's very difficult to differentiate what is each other. In this case, it's true that the number of particles in the box is smaller than this one, and then it looks like that this is different. But I told you I saw the images that it's not possible to differentiate by the eyes. You need to see what is the structure factor of this system, where the structure factor is the Fourier transform of the space, of the position in space. So if you go to the structure factor of the total disorder system, you get something like very similar to a Perkus jelly. You present this oscillation and this short range correlation peaks. But when you have a uniform medium, it's interesting that the structure factor goes to 0 below a given value. And this means, this is very interesting, below a critical K, the structure factor is equal to 0. And since the mean free path is proportional to the integral of the structure factor, this means that with the wavelength, the frequency is smaller than the half of the frequency of the cutoff frequency, the mean free path goes to infinity, and then this system is transparent. So even though the system is disordered, we have transparency. And for this reason, this medium are interesting, or the people are interested to generate this medium. And it's known that for generating this medium, this configuration are the equilibrium configuration when the pair interaction potential is equal to this function. It's a Bessel function divided by his argument. The thing is, the people generate this structure, but instead to use the potential real space, this is a bit of details, but they work in the reciprocal space and they generate the simulation. But if we want to do an experiment to generate this in a real experiment, we need to try to use the real space potential. And then we can try to fit to this potential to our system. This is again the silicon particle system in water. And this is the fitting that we did to get to this function. And we see that the fitting have only 4 spectral lines, or look very well, and the pattern is very, very similar. So maybe it's possible if we apply a random field with this property and do a molecular dynamic, we can get this uniform pattern. But before to try this tighter potential, we do some simulation, assuming that the real potential is this one. Only to know if the normal potential is the good, like at the testing, the testing example. And there is some problems. To summarize the problem, that we try to generate this structure using this real potential, not the fitting, the real potential that gives you to the stealthy uniform pattern, using a molecular dynamic and a spherical box with reflection boundary condition. And this we need to do that because the density should be constant, because the density depends on the critical K. There is some details that is not very interesting than now. The thing is, we try to do the molecular dynamic with 2,000 particles, more or less. The results, I show you here the structure factor of the system. This is the log scale of the structure factor, and this one is the normal scale of the structure factor. And both plots are there because in the first one we saw that in a low case, the structure factor is very similar to the structure factor of a sphere. It makes sense because the system is quite finite, but we can see that the structure factor goes very small and until one fluctuation that does go up. So it's not stealthy uniform, but we are going the way. The problem that we have is that it's not possible to see in the picture, but I can tell you that there is a layering effect. And there is a problem. The thing is that the system should be bigger to try to generate this system. So before to try to use our feet, we need to try to get the structure using this potential. And then right now we are developing implementation using periodic boundary condition to try to generate this system. And very interesting because you need a big system. You need the pressure of all the particles that are outside in order to get the good properties. The important thing is that we are able to fit to this potential. We need to do a further work in order to be able to really generate this potential using the real space potential. Well, I would like to finish only with another example. In the case that imagine that now we have our particles and we have a given potential, a given penetration potential. It's called like a U plus, depending on the distance, and it's associated to the energy density distribution. And we have another energy potential with another energy density distribution. So if we add both of them, we have another potential. But the energy potential, interesting thing, the energy potential should be always positive. It's always active. So the question is if it's possible to generate two different potentials in such a way that the total sun is equal to 0 in a given range of distance. So this means that the per-interaction potential is equal to 0, and we can go further in order to study the many-body interaction, or what is the effect of, what is the, for example, the equilibrium condition if the three-body potential are the dominant in your dynamics. And this is the idea. You have two potentials that are totally the opposite, and then try to get a 0 of the potential. We try to do that. This is the target, the objective, the aim, and this is the fit that we did. We can see that the sum of the sum is not 0, but it's relatively small. But the important thing that is smaller than KBT, and this maybe is enough to do a molecular dynamics and get a new distribution of a new equilibrium configuration. And then this is the idea we are looking for in order to study what is the effect of high order domination, high order interaction between your particles, no? In order to, for example, this is very pragmatic. It's possible to find new equilibrium configuration. For example, if the correlation function is different when the periodic interaction potential is equal to 0, or if the many body forces are the dominant one. And this is work in process. With this example of trying to get a 0 potential, but with energy density that is positive, I am in the end of the talk. Well, for take-home messages, it's true. I can say the random field is important. The random field induce optical forces that are conservative. I show you this expression that the random field, the potential is proportional to the energy density distribution and the property of your particle. And then we can try to place around what is the energy distribution in order to obtain a specific per-interaction potential, or in general, many-body interaction potential. It can be engineering by modifying what is the spectral density that we are using. And then the idea to engineering the potential is to use potential that are interesting in physical domain. For example, if we can get a potential that generates a steady uniform pattern, in principle, we can do it. We need to be able to solve all the problems in order to get a good system. And also, this could be a very good way to try to study dynamic when the per-interaction potential is equal to 0. That's all. So I want to say thank you so much for listening.
Okay, thank you so much, Diego. Is there any question in the audience? You've been asking questions in the meantime, but If not, a very quick question. So if I understood things correctly, you're using a scalar polarizability in your
In
description of your
principle, is
particles.
I use scalar, but can be any kind of polarizability.
And could you get any interesting effects, like simulating the effects of magnetic fields or magnetic dipoles or something more exotic that?
Well, it's possible because in the end, the DDA matrix is written here, the DDA matrix. Yeah, in the end, this polarizability can be any polarizability. This can be a tensor. And then you can play with chirality, you can play with magneto-optics. The thing is to...
You haven't
We didn't
tested
do it.
anything.
We didn't test
Okay.
it. And the thing is to know what can be interesting. Not
Yeah,
to say,
that's what I was asking, basically.
no, we didn't explore the derivation why it's interesting, but of course there is something very interesting.
Excellent. And
So why do you have to go to a zero potential through the sum and subtraction of two potentials?
Why I want to do that? Oh,
Why? So can you just use a zero potential?
the thing we need to get we want to get zero potential, but with energy in the system. Of course, if you don't have any field, the potential is zero, and then you don't have.
And you have to do it through that kind. So, but you could use any other potential that you would like.
Yeah, but the idea is if you give energy to the system, you have you have something that this is the per interaction potential. It's true that maybe there is no well explained, but if the idea is to get the two body, so the per interaction potential equal to zero, but with field, with giving energy to the system. So this means that we'll have another intervention of some many body particle intervention, and this is the idea to study this intervention. Because how do you think that how you can place a zero potential? The only thing I see in my mind is to have nothing on trying to.
But you could, I mean, so if you're fitting that, maybe you could use a bound. Say, okay, so the potential has to be zero, but the energy between the particles.
Okay.
No, I simply don't know. So it seems. It seems like a one odd possibility, no? Because you are taking those.
Yeah, of course. No, it's true that in this case we use the. Okay, maybe you say this. Why do you use this shape?
Well, the two things. I mean, so in the end, what you want is a zero
Yeah,
potential.
it's true. This is arbitrary. We started with a potential. I don't know why they say that this is okay, and then we take the example. But probably it's true. No, we can use any different potential. The idea is not if you are able to do a positive potential, it's difficult to do the negative to the constraint of the energy positive.
And one of the questions that Javi and I were discussing before, but so you have an homogeneous. So the random field is homogeneous. So this is
yes.
So it doesn't depend on any in the position of the one of the particles. That's why the potential just depends on the difference of the.
So the idea to use random field because they are homogeneous. It's true that it's not easy to get a real homogeneous field in a broad area, but yeah, the idea to use random field for that.
So the potentials only depend on the distance of the particles, but not on the position of the particle.
Yes, the thing when you have only this is it's true that maybe it's not well explained that all of the sample or the majority part of the sample I focus in the case will have only two particles, and then the force, since there is no any chirality, there is scalar polarizability, the force only depend or the potential only depend on the distance. And when you have more particles, it's true that depend on the distance of all particles. And in this case, we are cancel the per interaction potential. So you have only two particles, the potential is zero. But you have three particles, the two particle potential is zero, but you have another contribution given by the crosstalk between different.
But you cannot ensure that, no, because you're just calculating that for two particles.
Yes.
So if you use a third one, you don't know how.
No, yeah, because you can demonstrate that we have three particles. The total three particle potential can be equal to the two particle potential by a three particle potential. It's a generic for this kind of field. You can do this. You can do this. Indeed, we do something because for doing that we take for example we take the Tailor series for the log, and then we can grouping the 10 that only you have only there is only two particles, or the 10 that have three particles, the 10 have four particles, and doing that you see that the total potential can be seen like at the sum of the two particles, the sum of a 10 that only have 3 particles. And then if you are able to cancel 2 particles, you know that it doesn't matter how many particles you play, that the 2 particles is equal to 0.
Javi?
And how can you ensure that the solution is unique? Es unívoca.
Regarding the fit,
Obtaining the backward potential. There can be other combinations of randomness. Well, no, because it's homogeneous, right? Of spectral density and.
yeah, no, it's a good question. This unique, I have no idea. There is works. There is people. There is like a unique relationship between anybody potential with a two-body potential, but I don't know if it goes in the ratio.
There must be some theorem, because otherwise I wouldn't dare to say it's univocal.
Yes, no, it's a really good question.
All right. Well, if there are no more questions, it's almost 1. So thank you so much, Diego. And thank you all for your. Creo que no se ha compartido la pantalla en Zoom, pero bueno.
Lo puedo compartir aquí.
Bueno, hoy tengo una semana, Gabriel. Te he mandado.
Sí, lo he visto. No, que te contesté.
Mejor nos veamos a la vuelta.
Sí, tú hasta cuándo estás.
Yo estaría hasta el 7,
Vale,
8.
pero no me gusta esta de ir posponiéndolo porque al final lo hacemos.
Sí, no, que te está bien.
Esos días, te va bien.
Sí.
Ya, pues que hay un montón.
Yo a las 4 formalmente.
Alex, I will reply to you on the chat.
No tengo que ir a ningún lado.
Vale. No, te digo porque yo ahora tengo una semanita. Voy el jueves, porque es que si no encontraba hueco donde meterlo. ¿A dónde te vas? Relax total. No, eso no, pero tanto no, pero sí, está tranquilo.
Tengo que hacer una reunión contigo cuando voy
Ah, qué bueno.
¿Quieres saber?
Sí, vale, pues eso es muy importante. Vale. ¿Y cuándo quieres hacer física?
Tengo que saludar, porque venía un poco a la carrera.
Sí. ¿Y qué esas manejas?
Vale.
con ellos es
¿Qué preguntas online? Esto, o sea, ya moderna.
Mira, son agosto.
Demasiado lindo.
Vale, igual que hablo con Ricardo, a ver qué ocurrió el jueves, habla con Ricardo y a ver qué dice.
No sé hasta dónde, perdón. ¿Has contestado?
Sí.
Bueno, pues cerramos el Zoom.
Gira, o